in classical computing, we know there's a bit, there's a 0 bit and a 1 bit, and so I have a thing that holds charge, or not hold a charge, or can be up, or can be down, whatever you want to represent. It's a two-state system. In quantum computing, we also have the same thing. We have what we call a qubit. It can be in a state 0, it can be in state 1. However, it can be in a superposition of both. So our bit can be both a 1 and a 0 at the same time. And this is what the concept of qubit is. And so when we look at classical computing, we look at a particular gate. What does a gate do? A gate maps some array of zeros and ones to some array of zeros and ones. So we're going to do some kind of functional transformation from a set of zeros and ones to a set of zeros and ones. For the not gate, if I give a not 0, I get a 1. If I give a not 1, I get a 0. In quantum computing, what's interesting is your gates are unitary operators. And again, you can't waste energy. There is no heat loss. And so what I can do here is, because I have a superposition of zeros to ones, going to a superposition of zeros and ones, every function I have is computing all potential operations for the cost of one operation. So our NOT gate can take a qubit, which can be in a state of 0, 1, which is a superposition where I have energy, wave energy in both components. And when I run the NOT operation, I simply flip them. And so I computed with one step the not of 0 and the not of 1. I didn't have to do two operations, I only had to do one operation. And this is just not. Now I'm adding and sets of ands and whatnot. And so every quantum gate is a unitary operator. It preserves that wave function, it splits that wave function in some way. And not all gates, when you think about a quantum algorithm, you think about a quantum circuit, they don't all have to be the same operator. When we're doing our operations, they're all the Grover coin, or they're all Hadamard coin. However, you can have multiple different ways. As long as when that energy gets there, it just has to be split such that you conserve the total energy of that area of the system. And so how do gates connect to each other? Via wires. It's all vertices and edges. So you think of your vertices as these unitary operators, you think of your edges as just propagating wave energy. And so what does a quantum circuit do? And this is what I think, and no one talks in these notions, and this is what I've taken away from my time in this space, is to say you get the benefits of both breadth first and depth first computation at the exact same time. And so if you know what breadth first computation is basically, if I'm at, let's say I have a triangle going up, a hierarchy. If I do breadth first, I'm going to put one V here and one V there. And then it goes to 2 there, so I got 2, 2, 2, 2. And so I can constantly go down this tree by producing all these walkers at every branch of that tree with breadth first search. If I do a depth first search, I go all the way down one branch, and I come all the way back. And I go all the way down another branch, but then one over. And then I keep going down. With quantum computing, I get the benefit of breadth first search because I have all potential combinations of things happening at once. However, my answer is always going to be one depth first search answer. So what does that mean? So let's take this 5 qubit register. So I have these gremlins called qubits now. And they can both be either 0 or 1, or they can be both at the same time. So that's represent these 5 qubits, all 32 possible states, 2 to the 5, which is 32 possible states with one register. While in classical computing, I can only represent one of those 32 states at any one time. And I don't require all that memory. This is what's really important. I represent all those states in one state, even though I have 2 to the 5 states. And so this is where the multi-world interpretation of quantum mechanics comes in. How can I represent 32 different states in a 5-bit register? There must be multiple parallel worlds that exist where they all have different versions of these different states. I'm getting computing power for free. Where am I getting this power from? And this is where multi-world interpretation, the semantics of multi-world interpretation. So all these interpretations of quantum mechanics basically predict the same outcome. They just kind of have different interpretations of what's happening in the middle there. And the multi-world says, no, there's an infinite amount of worlds. And that's what their explanation is. And it kind of makes sense when you think about it in states. I have multiple states all represented by the same register. And then, what is the purpose of a quantum algorithm? So quantum algorithm, the whole point of it is to guide that wave such that I build up the probability so that in one particular state, which is my answer. I want when the wave function to collapse, I want to be 100% guaranteed that it collapses at the right answer. If all things being equal and it just collapses, then it's a random sampling of a particular answer. So a quantum wave function is trying to manipulate the wave function so that I get a nice strong peak of 100% right at that answer. So when I look at the system, it collapses, and that's my answer. And I don't think it's a probability, I know it's 100% certainty. And that's why I get first search. So while I can compute with all potential states, the problem with quantum computing is that when I go to get my answer, I only get one answer. I collapse that waveform. So that's where I become depth first at that point. But I hope that where it collapsed was the right part of the graph. Where's the right part of the answer? For quantum computing, while you get parallel computation for free, your solution, you only get one solution. You've got to make sure it collapses correctly. And so this is where the pilot wave interpretation of quantum mechanics comes from. Where pilot wave quantum mechanics says there is a particle, it just has a wave that surrounds it. That wave pushes it, it's like a guiding force. So while there's one answer, I just want to make sure while that wave's checking all these other areas, it's just constantly pushing the answer towards one particular direction. So it has a very depth-first interpretation when you think of the Bohm interpretation of the pilot wave theory. And so to iterate that point again, when I put all if I have a equivalent register, a 5-equivalent register, and I put it in the equal superposition, meaning that every bit is 0 or 1 with equal probability, the answer, or the state of those 32 numbers, if I was just to sample it right there, right at that point, I will have a 0.03 chance of getting any one of those particular answers, 1 divided by 32. And that's not good. That just means you're just throwing a dice. Your quantum algorithm is ultimately trying to make sure that you get a peak. You don't want a flat line. You want to, while you might want to start off in superposition, you want your quantum function, all those unitary operators you're applying to it, to peak it so that it collapses to the correct answer. And the way in which you do this is by controlling deconstructive and constructive interference as that wave function, as those gremlins propagating through your graph. And what I mean propagating through your graph, so when we look at quantum graph computing, well, your quantum circuit, your structure, the thing, your graph, is a bunch of unitary operators connected to each other. And then your process, your traversal, all of computer science can be described as structure and process. You have data structures and your algorithms. Well, our data structure here is this quantum circuit, it's a bunch of unitary operators connected to each other. And our process, our algorithm, is this wave function that we're diffusing over that particular graph, such that when we look at the graph, it's going to sample the right vertex. And that's our answer to that question.
I would say that there's an energy component in your vectors that is not represented in, at least is not presented here, that is not being destroyed in your superposition. We're just showing amplitude.
Yes.
And then there's some peaking finite energy.
Yes.
I'm going back to another particle theory, like an energy for particle wave function. You're handling the wave function pretty well, but I'm not seeing how you're preserving the energy of the particle.
If I was to, at any time I had, I have a whole bunch of gremlins with like a 2-array vector brought on the line, and they have some components of that 1.0 from the beginning. If I was to take that unitary operator, the Hadamard, and do a transpose of it, and multiply it by that system again, it would just reverse it. So if I went 50 steps out, and I did transpose and multiplied 50 times steps again, it'd all go back to 1, 0 right in the middle. So it's reversible. And because it's reversible, that means that it loses information. So all these operations, what's really cool, and I talk about it in the paper, is that I just do the operator in reverse and just run the algorithm in reverse and it back to my initial state. So I can just roll everything back up. So that's how you get
do you have any interesting results so far on sort of convergence rates based on the type of system? How many iterations you have to do in order to get the probability distribution?
Yeah, so I really wanted to get into doing practical algorithms with this, and when I heard about graph data, okay, I can do some quantum stuff. I've been kind of like just dabbling. I thought I was going to be able to use practical algorithms, but I never got to that point. It was actually very difficult for me to learn all this at the same time as well as present on it. But yeah, there's a few algorithms. I mean, there's like Shor's algorithm and Grover's search algorithm, and for like Shor's algorithm, which is how you find prime numbers that make up a very large number, is always good. Decomposable to prime. That's how like the security systems work, SSH and kind of RSA or factoring kind of problems. And so what's really interesting about those is they will just run these unitary operators on some particular number represented qubit, such that they're going to find the prime factors, at least one of the prime factors, and then they're going to easily write the other ones. And they need to make sure if you run it too many steps, then it's going to be converging with 1.0, and you're like, okay, sweet. You cannot look at that, so you just have to know theoretically that you're about to get a peak. If you do one more step after that, it starts to break apart. So there's not like kind of conversion. It just sits nicely. It's you have to really time when you're going to look at the system. So the Shor's algorithm, which is like the holy grail upon computing, it's like wow, we can factor numbers that are NP complete and like or NP complete exponentially takes not time. We can do that extremely fast. I forget what the worse than linear, but we can do it extremely fast. They just know that it's not as simple as just saying, okay, it's going to converge now and look. You have to time it perfectly, or else that wave just starts to break apart. And it has to do with like harmonics of prime numbers. It's a really crazy algorithm. I don't quite understand it, but they just know that you're going to get this prime numbers get hit every once in a while through these harmonics, because there's these energy flows that are going through these numbers, these qubit registers, and you have to hit it at the right time. It's in the right phase of its evolution, and that's it. It's really creepy. Yeah.
So if I understood correctly, and my takeaway is that there's this natural phenomenon that you're explaining, and you explain how you can simulate that with graphs, or represent it as graphs, and then simulate it with Gremlin in this case.
Yep.
So did I have that right?
Yep.
Okay. So I understood you talking.
Oh, okay. Sorry, there is no I'm not cheating computation like now we're doing quantum computing. It's all simulation. It's expensive. We're in a classical world.
So my question, and this is, I mean, the real world. I mean, in science, you have the scientific method. You do your observations, and you make your observations. You sit down, you come up with your theory, hypothesis, go to experiments, and do everything.
Yeah.
But in computer science, right, those two worlds really collapse to one thing, which is the physical machine, the computer, right?
Yep.
And on this computer is where we make our observations, but at the same time we make our experiments.
Yeah.
So it seems here that now you're seeing all these computational material science and computational chemistry and stuff.
Yeah.
So what are the things that we can now do computationally using this type of simulation where I don't have to go and set up the lab to do anything?
Exactly.
So
What's really cool about this is at every time step, I can create that probability distribution. If I wanted to create the probability distribution of the wave function, I'd ultimately be collapsing it. And so in physics, if I want to, at every step of my line walk, I was showing you what the plot looks like, and I show you what the plot looks like. You can't do that in physics. All I can show you what the plot looks like at the end and at the beginning. And so then they have to infer through massive amount of experimentation what that distribution was doing over time. And so it took them forever, and that's what Schrodinger's wave equation is. It's like, okay, I do this experiment, and I get that. And then they have to just figure out, oh, it's a wave that's undulating, and they have to figure out what the phases are and all this crazy stuff. And they go, holy shit, it took us for years to figure out what this algorithm is. And what's nice about Gremlin, or not Gremlin, but just computers, is I'm not really doing a quantum computation. I'm not using physics. I'm not using reality to do quantum computation. So I can look at that waveform as it's going from classical state through wave state back into classical state. So you can really explore and experiment and try different coins and see how things evolve. So if you want to do Shor's algorithm, I really wish I got into it, but I didn't understand it. I still don't understand it at this time, but I'd love to show Shor's algorithm, how the wave function is just modulating and say, look, now we get this cool harmonic. And so always at step number 20, let's assume, then I want to look at it and then I'll get my answer. And so you can study algorithms without having to use.
So what would a theoretical physicist say about this? So I'm thinking like from the biological perspective, right? You come up with you're in the wet lab and you say, I do something computational and I come up with a putative gene or something, but they don't believe it until it comes out in the wet lab. And you know what? In the wet lab, it's not as trustworthy as you did computationally, but I still don't trust it because I need to see it myself. So does that happen also here with like theoretical physicists?
Well, what's really nice now is that Gremlin can be used as a quantum computing language. So every time I do these unitary operators in Gremlin, that's just doing a unitary operator in the real world. So a quantum chip, if I had a quantum chip, Gremlin in theory, Gremlin's a Turing-complete language. It can do any kind of computation you want. So, and while I'm doing quantum computation in the classical world, where I'm actually, every time I do a split, I have to represent each individual thing and compute each individual thing. If I have a quantum chip, I can just use Gremlin as a language, which defines the data flow for how that wave disseminates through space. So for quantum physicists, they might be like, sweet, I have a programming language now that allows me to represent waves, diffuse waves, and collapsed waves. And so this could be a language for quantum chips. Because quantum computing and Gremlin are very similar. They're both data flow languages. They're energy diffusion languages or flow languages. And so they kind of semantics map really nicely, where you're just thinking, just propagating energy and just breaking apart that energy as it goes. So it has kind of a nice mapping to the real world.
What are you going to add to or fix in Gremlin now that you've done all this fun stuff?
Oh, it's crazy, a whole bunch of stuff I looked at. Bulking, so bulking, what's really the problematic with SACs, so the concept of SACs, when in Gremlin, there's an optimization in Gremlin that when two Gremlins exist at the same vertex, I say, well, I don't need to represent two Gremlins, I just make one Gremlin that has a count of 2. And so I can do some nasty path computations with Gremlin, calculate a gajillion amount of paths, and then it's like, how am I doing that in milliseconds? Because I'm bulking Gremlins. Yeah. So anytime I don't need to represent multiple objects, I create one object and just have a long counter. The problem is I made it a long counter, so I cannot do negative energy. So my new concept for Gremlin moving forward is bulking. The bulking construct is going to be pluggable. So one of the problems I've had with Gremlin is when I do things with Spark, when I do Gremlin over Spark and running a massive computation, I easily blow the long space. 2 to the 64 bits is like that happens quite fast. So I'm like, crap. So what I really want to do is I'd love to have a big integer. But the problem with big integers is a very expensive data structure. So I said, okay, well, let's push that off and keep it longs, and you might get an overflow, and that sucks. What I'm going to do in the future of Gremlin is to say, okay, well, now you can have different kind of bulking operators, where one of them could be complex numbers, one of them could be arrays, one of them could be longs, one could be big integers. What's another interesting I discovered when I first was doing this stuff, and the reason Jen's on this paper, Jen's my wife, and the reason she's on this paper, she figured out what I was doing wrong in the algorithm. What I was learning was that when I was propagating energy, I didn't know how to get negative values. And I was all doing these long-term computations. What I realized that if I made that lattice big enough, that I would blow long space, and when I blew long space, it went negative. Right. So what I was thinking was, I think what happened is that the real world has a fidelity issue, doesn't have enough bits to represent how much energy is in a space, and that's why energy undulates. So one of the questions I want to explore is, can I represent all of quantum computing by just saying you have bit overflow issues? And that's why you have negative values, and that's why there's a wave. It's because it's actually a computer we're running on, and you get a negative value because of overflow in a long space.
I'll drink to that.
Yeah. No, I mean, this is all very new. So Z-Wave is a computer out of the company, I don't know where they are, but Google had bought it, NASA had bought a machine, and they have a quantum computer that's a type of simulating simulation it can do extremely fast. It's a really specific type of algorithm that can do. General purpose computing with bits of superposition is extremely, it's very difficult. We don't have like the techniques right now to keep things in superposition without the equilibrium collapsing. The holy grail would be like, once we can keep things in superposition for indefinitely, there's going to be a need for programming language. Oh, they are moving in a field. What's your one particular part, one particular bacteria, or multiple bacteria? Oh, multiple bacteria. Yeah, I mean, so all this is fields. I mean, that's what we're simulating are just fields. I don't know your particular brother's line of work. What there is somebody, and I can give you, I don't know his name, I can look it up, but there's one guy who knows how to put a piece of bacteria into superposition, so it can interfere. Just like the continuous light source of the candle, that is, that's the herd, like we were saying, like you're saying, multiple bacteria. And then you can say a single point, well, it still acts like a herd. And so this guy who can put a bacteria, it's all this weird stuff about, just how 0 degree Kelvin, blah, 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 blah. I mean, it's a lot of like machinery, but he can put a piece of bacteria so that it interferes with itself and might have the exact same patterns as the herd patterns in multiple systems. And that, I mean, there's a huge overlap. So if you're interested, email me and I'll give you that guy's paper and send it to both. Yep.
So in answer to an earlier question, I think theorists would welcome this as a computational framework to simulate quantum circuits, most notably because of the distributed aspect of this. Those problems you're talking about are super exponential in size. When you're talking about a number of qubits, you're talking about usually 2 to the number of qubits is the dimensionality of the problem. So in previous, simulations of all this stuff, you blow up in space like crazy in no time.
Yeah.
So you were happy to do 6-qubit simulations of some of these algorithms, but if you can do it in a graph in a distributed framework like this, you can blow that up.
No, check this out. So what's really cool is that when you look at how, if I take a lattice, and because of how bolting works in gremlin, when two gremlins come together, they'll superimpose to each other, and either the energy will go up or the energy goes down. So at the limit, the amount of gremlins that you actually have to represent is the number of vertices in the graph. So you think of a whole bunch of gremlins just covering that graph, and there's like a rubber sheet going up and down, up and down. So you can model of that wave function without having this exponential explosion with all these different paths, because it's just one. They keep just propagating energy back and forth to each other.
But even if you do, the tools that people have used to do this before don't distribute like a nice graph.
Well, yeah, that's really cool. So if you do this like on Spark, so Gremlin, what's really nice about Gremlin is that it compiles down to OLTP systems or overlap systems. So it's the exact same query language. If you want to have like a billion-edge graph or a trillion-edge graph, you can just load that up into Spark, and what happens is you're going to have a trillion little gremlins that are just going to be undulating in one space, and that's actually a very easy computation. That's not too hard for Gremlin to do. So I can do very large spaces, very complex wave dynamics. And yes, I mean, this is not something that Gremlin does. I have a couple tricks I've done to make the compression really nice, but anyone can do this with passive repeaters. It's just, you just have to say like, holy crap, I can do this kind of compression. I can use tools like Spark and multiple computers and all these cool tools that we know how to use, where a guy in a lab who just uses R and says, oh, I'm just kind of stuck with R, it's C on my laptop, and that's all I got. He doesn't know how to compress things and do this kind of stuff so that he just blows his heap all the time. What's really nice with Gremlin, I'll make sure that it's always going to be efficient.
So in your paper, you referenced Amazon,
Yeah.
and that's where you have to look for the 1 trillion. That's probably internal with them, proprietary, or any.
No, they released it. Yeah, I don't know much about it. So their invoicing network is what they have. It's like their, what's that? Oh, fulfillment network. I might be lying, but I think what it is it's basically anytime someone orders something and what delivery truck is going on and when it was delivered, it's just kind of their keeping state of packages being delivered. That graph is close to 1 trillion edges, and they represent that in Titan, and they use Gremlin to do your package.
What else they use? Spark? Or?
No, because OLTP, so I'm not sure what this. However, they just upgraded to the top 3, which now provides a lot of Spark computation. And so they actually released Titan over DynaMod, which is what they use to represent all that stuff. It's on GitHub. Yeah. Awesome. And it's one of their servers. AWS provides Titan as one of their servers. Yep. Oh, you're just stretching. Okay, so if I pull the source back a little bit further, or if I made the slits this big, or if I put the slits together or this far apart, or I use a different point, I get different interference patterns. And so if you look on like Wikipedia, you always see this beautiful kind of pattern like that. And so I just tweaked with it until I got that exact same pattern. I mean, that's how it is. I mean, certain particles are going to do certain things, and I don't know the distance and whatnot. So it was just me just fudging with the structure to make sure I got that. So when you go into Wikipedia, you go, what? You go, oh, that's always different interference patterns. But sometimes, the peak would be inverted or something like that. Yep.
So the slits are important because you're interacting with the universe. So what is the expectation of how you're going to model particle interaction? So you've got one particle, you shoot it out there, it hits some walls, but in the quantum world, there are actually interactions going on with the wall.
Yes.
Right? To make these reactions happen. So you model it very simply. What happens when I now have another particle coming by that also interacts? And it happens to send some other field actions, and we've got pretty soon we have virtual particles popping in and out, and the Higgs shows up. Okay, life is good.
This is like the dirty secret of quantum mechanics. It's called the 3n problem. And so when you have a single particle, n is 1, and so the dimensionality of the space is going to be 3. And so that wave function is going to tell you where in xyz coordinate that particular particle is going to collapse to. If I have two particles, the wave function is not evolving in 3D space. It's evolving in 6D space. And so they think that the universe, and this is a huge debate, is called, the universe is 3n, where n, the amount of dimensions in the universe is 3n, where n is the number of particles in the universe. It's in massive space. So they call the wave function like a block. It's just one, it's a configuration space. And when you sample it, it's going to read off where every particular particle is. It's a configuration or a state space. And then that just says, okay, all the particles are here. And that's the world that we see. And so actually the wave function is not just a wave function evolving in 3D space. It's evolving in a very high dimensional space. When you do single particles, that n is 1, so it's 3D. And that's why you can get away with this. And the reason why we can't decouple, say there's two waves interacting, is because of entanglement. And so entanglement gives you this weird property, such that if I know where one particular particle is going to be, where it is, I know exactly where another one is. That's because their wave function is actually one wave function. So we don't understand, it makes no freaking sense that the universe is just this wave undulating in 3D space. It's a massive space. And then it's just been basically, the wave function is an index lookup to say where every particular particle is. It's a hash map. And it's like the most weird function where you say, okay, it collapses, and that's a pointer, and that pointer says that every particle is here, and then it goes to the next one, now it's here. And there's no actually reason why 2 points in that wave function space are adjacent to each other. And the only reason we know this is just because of experimental data. We say actually the space is evolving, and it's evolving like this, and all these different kinds of coins. Figuring all that stuff out is a huge problem in physics, where they'll get these results, and then they say, okay, well then now the space is looks like this, and these are the operators that are having it, and we just don't know why. And so philosophers are like, holy shit, we think that space is not real. This is just an illusion that we live in 3D space. It's actually this massive dimensionality, and there's just one wave function, and then we just keep collapsing every time we open our eyes. Anybody else? Yeah, we have one more and then we gotta go. Yeah, I mean, I saw a bunch of that stuff on the web. I never got into it that time. Cool. Thanks, everybody.